Welcome to this explainer. Today, we're going to demystify the mechanics of electrolysis and basically hand you the ultimate set of rules to master this entire chemistry puzzle. I mean, if you've ever stared at a beaker with electrodes bubbling away and thought, how on earth do scientists actually predict what's going to happen in there? Well, you're in exactly the right place. We're about to break down that invisible flow of electrons and ions into a clear, really straightforward story. Okay, so here's our game plan. We've broken this journey down into 6 totally manageable steps. We'll start with the basic rules to get our foundation rock solid, look at both Molten and Aqueous solutions, figure out how to actually predict the products, see how all this scales up in the real world, and then wrap up with a real exam question to test your knowledge. All right, Section 1, Unlocking Electrolysis Basics. Before we can start predicting the winners of our chemical reactions, we absolutely need to know who the players are.
So electrolysis literally translates to splitting with electricity. But there is a massive catch here. The ionic compound we're working with must be either melted, which we call molten, or dissolved in water, which we call aqueous. And you might be wondering, why? Well, it's because in a solid state, those ions are just locked tight in a rigid lattice. By melting or dissolving the compound, we're freeing up those charged ions so they can actually move around and play the game the second we switch the electricity on.
Now, I know the vocabulary can get a little overwhelming, but notice how these soft pastel blue and green colors kind of help map out the chaos. It's actually a very elegant system. The electrolyte is our liquid arena. The electricity itself enters and exits through rods called electrodes. Specifically, the positive electrode is the anode, and the negative one is the cathode. As for our moving pieces, the positive ions are cations, and the negative ions are anions. Just take a mental snapshot of how those terms pair up. So, how do these mechanics actually play out once the juice is flowing? It all boils down to one of the most fundamental rules of the universe. Opposites attract. Those positively charged cations make an absolute beeline for the negatively charged cathode. And when they arrive, they undergo reduction, meaning they gain electrons. Meanwhile, the negatively charged anions rush right over to the positively charged anode to undergo oxidation, literally just handing their extra electrons over. To lock this in, you've got to remember the golden rule of electrolysis, oil rig. Set against this really calming sunset orange, this is the one mnemonic you should permanently anchor in your mind. Oxidation is loss of electrons. Reduction is gain of electrons. Seriously, whenever you get stuck on a problem, just write oil rig at the top of your page and let it guide you. Moving right along to Section 2, How Molten Electrolysis Works. With our basic vocabulary totally locked in, let's start with the simplest environment possible. In a purely molten state, there is no water around to complicate things. It's literally just the pure, melted compound. Take molten lead bromine, for example. It just splits perfectly into solid lead metal at the negative cathode and this brown bromine gas at the positive anode. Same goes for sodium chloride. It divides neatly into pure sodium metal and chlorine gas. Because there are only 2 ions present in the whole beaker, there's absolutely zero competition. It is a completely straightforward split.
Section 3, the aqueous solution twist. Okay, what happens when we don't melt our compound, but instead we dissolve it in water? This is where electrolysis gets incredibly fascinating and, frankly, a bit more crowded.
Suddenly, our arena is packed because water actually brings its own players to the game. Water naturally dissociates just a tiny bit into hydrogen ions and hydroxide ions. So in aqueous sodium chloride, we don't just have sodium and chloride hanging around. We've actually got 4 ions competing at the electrodes. We have sodium and hydrogen both racing toward the cathode, and chloride and hydroxide both rushing to the anode. Which brings us to Section 4, Rules for Predicting Products. Since we've got multiple ions competing, we desperately need a set of tiebreaker rules to predict who actually wins. Let's start at the cathode. The rule here is that the less reactive element wins the right to be discharged. It's kind of like a chemical stubbornness contest. Highly reactive metals, like sodium or potassium, are super happy staying right there in the solution as dissolved ions. So they lose out to hydrogen, meaning hydrogen gas bubbles off instead. But unreactive metals, like copper, silver, or gold, they desperately want to turn back into solid metals, so they beat hydrogen and form a shiny metal coating right on the electrode. And here is your ultimate cheat sheet for that, the reactivity series. Notice how hydrogen acts as this vital dividing line right there towards the end? That's your key for cathode predictions. Everything to the left of hydrogen is highly reactive, so in an aqueous solution, hydrogen gas is going to win out. But everything to the right,
copper, silver, gold, they'll successfully coat the cathode. Meanwhile, over at the anode, where our negative ions are battling it out, the rule is surprisingly straightforward. If a simple halide is present in the mix, meaning chloride, bromide, or iodide, it wins hands down, forming a halogen gas. But if there is no halide present, like if you have a big complex sulfate or nitrate ion instead, then the hydroxide ions from the water step up to the plate, discharge, and produce oxygen gas.
Okay, let's see these rules in action with aqueous copper sulfate. We've got our 4 ions. At the cathode, copper is going head-to-head with hydrogen. Because copper is less reactive, it wins. Solid copper gets deposited. Over at the anode, sulfate is competing with hydroxide. Since sulfate is definitely not a halide, hydroxide wins the tiebreaker by default, and oxygen gas is produced. See? It's perfectly logical once you know the rules.
Section 5. Real-world electrolysis applications. We've totally mastered the beaker scale, so let's scale this up to massive industrial operations. This isn't just some lab trick, it's literally the backbone of global manufacturing.
Take brine, for example. Brine is just highly concentrated aqueous sodium chloride, so super salty water. Electrifying it creates 3 completely distinct, highly valuable industrial products. Because sodium is too reactive to form, we get hydrogen gas at the cathode, which we use for fuel. We get chlorine gas at the anode, which is absolutely essential for water treatment and making PVC pipes. And what's left swimming in the solution? Sodium hydroxide. That's the foundational ingredient for manufacturing soak. One single process, 3 massive industries.
We also rely on electrolysis to extract aluminum. Aluminum is way too reactive to be extracted using traditional carbon smelting, so we actually melt aluminum oxide. And to save a ton of energy, we dissolve it in molten cryolate to lower its melting point. At the cathode, we get beautiful liquid aluminum metal. But here's a wild quirk. At the anode, oxygen gas is produced. And because the industrial anodes are made of solid carbon and the whole environment is incredibly hot, that oxygen literally reacts with the carbon anodes to form carbon dioxide, meaning those massive solid anodes just burn away over time and have to be constantly replaced.
Finally, Section 6, Acing the Chemistry Exam. Let's make sure you are totally prepared to dominate this topic in any testing environment. Before you sit down for a test, you need to lock this checklist into your brain. Always trace the charge. Cations go to the negative cathode, anions go to the positive anode. Remember your oil rig. Reduction happens at the cathode, oxidation at the anode. And the biggest trap that catches students off guard, forgetting that water brings those sneaky hydrogen and hydroxide ions into aqueous solutions, just remember, if there's a halide, it wins the anode. If the metal is less reactive than hydrogen, it wins the cathode. So let's put your new knowledge to the ultimate test with a classic EdXL IGCSE question. You have aqueous copper chloride. Think about those 4 ions. Think about the tiebreaker rules. At the cathode, copper is less reactive than hydrogen, so copper forms. At the anode, chloride is a simple halide, so chlorine gas forms. Boom. You've just unlocked the invisible mechanics of electrolysis. The real question is, now that you understand exactly how to tear compounds apart at an atomic level, what other invisible forces in the chemical world are you ready to conquer next?